Hello, welcome back to my Physics 100 class. Today we will study about light and optics. This subject is very important since it is related to our daily life and also one of the foundation of modern technology, such as fiber optics for your internet connection, laser, LED display, touchscreen display in your smartphone, space observation with Hubble telescope, or even a future technology such as quantum carbon dots biosensor or cloaking device technology using metamaterials, which allows you to stay invisible from everybody. The propagation of light from the light source can be modeled in terms of wavefront. At a long distance, the wavefront is assumed to be plane wave, where the trajectory of rays parallel with each other. This assumption will help us in solving the image formation of mirror and lens by using a simple geometrical model. The simplest rule of light is the law of reflection. Consider a plane such as a mirror with the orientation indicated by the normal factor perpendicular to the plane. When the incoming light arrives at an angle theta I relative to the normal factor, then it will be reflected with the same angle theta r. Based on the reflected light, there are two types of reflection, specular and diffuse reflection. In both cases, the law of reflection is still obeyed. In the specular reflection, the image produced by the smooth surface is clear, since the reflected waves are parallel with each other as a result of single orientation of the plane. In the diffuse reflection, we have a randomly reflected light due to the random orientation of the planes, which is not smooth. For a plane mirror, the image produced by the mirror has some properties. First, the orientation of the image is upright. Second, the image height equal to the object height. Third, the distance from the mirror to the image equal to the distance from the mirror to the object. Fourth, the left and right side of the image is flipped as compared to the actual object. Fifth, the image is virtual, which means that image cannot be seen on the screen behind the mirror. These pictures describe the image formation from a plane mirror. The image formation of a mirror based on the reflection. So the law of reflection must be obeyed here. The spherical mirror. The inside of the spherical surface creates a concave mirror, while the outside of the spherical surface creates a convex mirror. The main or principal axis is actually the straight line passing through the middle of the sphere. And keeping that in mind, anything in front of the mirror is real and positive, and you need to use a solid line to draw the ray trajectory. And anything, could be image or the distance, in the back of the mirror is virtual and negative, and you need to use a dashed line to draw the ray trajectory. For a concave mirror, the focal length is half of the spherical radius, and the focal point is located in front of the mirror. So for a concave mirror, the value of the focal length is positive half times r. To draw the image formation in a concave mirror, there are some rules that need to be followed. Rule number 1. The incoming ray, which is parallel to the main axis, reflected to the focal point. And rule number 2. The incoming ray, which is aimed to the focal point, reflected parallel to the main axis. And the last one, rule number 3. The incoming ray travels toward the center of the curvature, reflected back on the same path. To draw the image formation from the convex mirror, we have to follow these 3 rules. The first rule is the incoming ray, which is parallel to the main axis, reflected as if originating from the focal point. And rule number 2, the incoming ray, which is aimed to the focal point, reflected parallel to the main axis. And the last one, rule number 3, the incoming ray travels toward the center of the curvature, reflected back on the same path. Since in the convex mirror, the focal point is located behind the mirror, so the focal length of the convex mirror is negative half times r. Using a simple geometric model, we can determine the magnification formula for a spherical mirror. M is the magnification factor equal to Hi divided by Ho, in which Hi is the height of the image and Ho is the height of the actual object. M is also equal to minus Di divided by Do, where Di is the distance of the image to the mirror and Do is the distance of the object to the mirror. The simple equation for the spherical mirror is 1 over F equal to 1 over Do plus 1 over Di. Later, we will also learn about the lens, and they also use the same formula. We can summarize here some conventions for the mirror. The focal length is positive for the concave mirror, and the focal length is negative for the convex mirror. Do, the distance of the object, is always positive, and it's located in front of the mirror. Di, the distance of the image, is positive whenever the image is formed in front of the mirror, and Di is negative whenever the image is formed behind the mirror. Dashed line represents virtual ray, and it's located behind the mirror. The solid line represents real ray, and it's located in front of the mirror. This is the example of problem correspond to spherical mirror. A 2 cm high object is placed 7.1 cm from a concave mirror whose radius of curvature is 10.2 cm. Find the location of the image, and B, its size, and C, the image is upright or inverted, and D, draw the light rays. In this case, I will only do the first part, finding the location of the image using the mirror's formula. Since we have a concave mirror, the focal length is positive, and the value of the focal length is half of the radius of curvature. So the focal length is 5.1 cm. By putting all those numbers in the mirror's formula, 1 over 5.1 equal to 1 over 7.1 plus 1 over Di. Solving this equation, then you can get the Di, the distance of the image, about 3 cm. When the light falls on the surface of a particular media, it can be reflected or refracted through the media. The velocity of light in the open air or vacuum is higher as compared to the velocity of the light inside the media. Refractive index which characterize the media, is basically the ratio of the velocity of light in the vacuum and the velocity of light in the medium. The law of refraction is called as Sahal-Snell's law, after Ibn Sahal and Snellius. The incident ray from medium 1 at an angle θ1 will be refracted or transmitted with the bending angle of θ2. According to Sahal-Snell's law, n1 times sin θ1 is equal to n2 sin θ2. If the incoming ray originated from the medium with a lower refractive index, the refracted light will be bent toward the normal line. On the other hand, if the incoming ray originated from the medium with a higher refractive index, the refracted light will be bent away from the normal line. Due to the effect of refraction, the apparent depth that you see is lower as compared to the actual depth. Using a simple geometrical model derived from the Sahal-Snell's law, we can determine the apparent depth by this formula. D prime is equal to D times n2 divided by n1, where D prime is the apparent depth and D is the actual depth, n2 is the refractive index of medium 2, and n1 is the refractive index of medium 1. When light travels from a dense medium to a less dense medium at a particular incoming angle, all light will be reflected back inside the medium and none refracted to the second medium. This phenomena is called as the total internal reflection. The critical angle is equal to the ratio of the refractive index of the less dense medium and the denser medium. The application of the total internal reflection can be found in fiber optic technology. In a fiber optic technology, all the information such as data, movie, or audio carried by the light ray. The light ray transmitted inside the fiber optic and following the total internal reflection condition. In that way, there will be no loss of information since the light is trapped inside the fiber optic. When the white light falls on the surface of a prism, all the components of the white light will be dispersed and separated from another with different angles and colors. As you can see in the table, each color corresponds to a specific refractive index and wavelength. The rainbow color that you see in the sky is actually the dispersion of the sunlight by the water droplet in the sky. The optical instrument that you are familiar with are lenses. Unlike mirror, which has a single focal point only, lens has two focal points. And based on their shapes, we have two different groups, the converging lens and the diverging lens. As compared to the mirror, lens is different. Lens has two spherical sides, thus a lens has two focal points. In lens, image is virtual whenever the object and the image are located in the same side of the lens. The dashed line should be used in the ray tracing method for the virtual image. The image is real whenever the object and the image are located in the opposite side of the lens. The solid line should be used in the ray tracing method for this case. The ray diagram in lens. The image formation by the converging lens must follow several rules. The first rule, the incoming ray which is parallel to the main axis refracted to the focal point on the other side of lens. The incoming ray which is aimed to the focal point refracted parallel to the main axis. And the last one, the incoming ray which passed the center of the lens refracted back along the same trajectory. This is the image formation from a positive lens. For example, the lens here is coming from the camera. This is the analog camera. It's not the digital camera. Using the first rule, the incoming ray, which is parallel to the main axis, will be refracted to the focal point, and the incoming ray, which is aimed to the focal point, will be refracted parallel to the main axis, and the incoming ray, which pass the center of the lens, will be refracted following the same path. As you can see here, the image formed from the positive lens is real, and the orientation is inverted. So, for the positive lens, image is real whenever the object and the image are located in the opposite side of the lens, and the solid line should be used in the ray tracing method. So as you can see here, the object and the image are located in the different side of the lens, so the image is real. This is another example of image formation by a positive lens. If you put the object closer than the focal point, the image form is virtual. So the image is virtual whenever the object and the image are located in the same side of the lens. The dashed line should be used in the ray tracing method. So as you can see here, the object is put on this distance which is closer as compared to the focal point, and the light that the incoming ray, which is parallel to the main axis, will be refracted to the focal point, and the light which pass the center of the lens will be refracted along the same line. Those two red lines doesn't meet with each other, but if we retrace these lines to the right side, so you see the crossing of those lines. So now you can draw the virtual image here. Since the location of the object and the image is in the same side of the lens, so the image is virtual, and you have to draw the image and the ray tracing line here using a dashed line. The image formation by a negative lens must follow the same rules. The incoming ray, which is parallel to the main axis, will be refracted as if originating from the focal point, and the incoming ray, which passed the center of the lens, must follow the same trajectory. Both lines cross with each other at one point here. So you can draw the image here. Since the object and the image are located in the same side of the lens, so the image here is virtual. And the properties of the image here is virtual, upright, and shrunk. The lens magnification equation is identical to the spherical mirror equation. So you use the same equation, 1 over dO plus 1 over di equal to 1 over f. And the magnification M is equal to Hi divided by Ho and equal to minus di over dO. Here's the example of the image formation by lens. A person with a height 1.7 meter, the focus of the camera is 0.050 meter. Find the distance of image and find the magnification and height of image. 1 over di equal to 1 over f minus 1 over dO. So di is 0.0510 meter. When you check the magnification, m equal to minus di over dO equal to minus 0.0510 divided by 2.5, and that's equal to minus 0.0204. So the height of the image will be m times h naught, which is equal to minus 0.0347. So here's some convention that you can use for the image formation by lens. Real image can be seen on the screen. Virtual image cannot be seen on the screen. Focal length is positive for the converging lens, and focal length is negative for the diverging lens. dO, the distance of the object, is positive whenever the object is put in front of the lens. di is positive for an image formed in the opposite side of the object, and di is negative for an image formed in the same side of the object. M is positive for an image that is upright with respect to the object, and M is negative for an image that is inverted with the respect to the object. Okay, that's our lecture today. Then you can do some exercise after this. And thank you. See you later.